All right, the time has come for us to begin to prove some theorems. Today we'll prove the triangle exterior angle inequality, and then on the basis of that we'll prove a number of parallel tests, which will allow us to say that when certain conditions are met, lines are parallel. Now, the triangle exterior angle inequality, when we encounter it, I don't think you'll find the proof particularly difficult, but I think, or I suspect your initial reaction will be, yes, this is true, but why is this so very important? And all I can say about that is you will see. Let me mention as well that the way that we approach the subject is exactly the way that Euclid approached it. The triangle exterior angle inequality is a theorem from Euclid's Elements, and then we'll prove the parallel tests based upon it in very much the way that he did. All right, so first of all, of course, we need a definition of exterior angle. That's not a concept that we've seen before. So imagine that we have a triangle and that we extend one of the sides through a vertex. When we do this, we create an exterior angle. It's an angle, as it were, outside the triangle, adjacent to one of the interior angles. And of course forms a linear pair with that interior angle. So you can see in the diagram that I've extended a side, the base, through the right. The extension I made dash just to emphasize it, and that created the exterior angle number 1. Now, of course, we can create multiple exterior angles in a triangle. As a matter of fact, we can create 2 per vertex, because at every vertex, 2 sides come together, so we can extend either of those sides and create a pair of exterior angles. You might notice, however, this is not particularly important, but I'll mention it, that the 2 exterior angles at a vertex are, of course, vertical. So, of course, they're equal to one another. So whatever else we can say about about exterior angles, we can say the 2 exterior angles at a vertex are equal to one another. Now, we won't talk about exterior angles just in isolation, but rather we'll talk about the relationship that an exterior angle has to its remote angles. And the remote angles for an exterior angle are 2 of the interior angles of the triangle, the 2 to which the exterior angle is not adjacent. So as you see in my diagram, where I've shown only one, or named only one exterior angle per vertex, for exterior angle number 1, the interior angles to which one is not adjacent are 4 and 6. So for angle 1, 4 and 6 are the remotes. Likewise for angle 2, the remotes are 4 and 5. And for angle 3, the remotes are 5 and 6. So which 2 angles of a triangle are the remote angles? Of course, that's a relative matter. And what it's relative to is your choice of exterior angle. Now, here's the theorem. I like to think of this as a kind of sleeper theorem. Far from apparent, as I said a moment ago, why it is so extremely important, but you will see. And here's what it says. And it's an inequality. In a later chapter, we'll study or we'll prove a number of theorems that are all ultimately inequalities. And this is the first of them. And much of our later work on inequalities will depend upon this one. And it says this. The measure of an exterior angle of the triangle is greater than the measure of either of its remotes. So do make sure that you understand what this says. It doesn't say that the exterior angle is greater than the sum of its remotes. I've had students misunderstand and think that it says that. Instead, it means this. Consider the relationship of an exterior angle first to one of its remotes and then to the other remote. It is greater than the first, and it is also greater than the second. All right, so as for how you prove this, well, of course, we have to create an exterior angle. So we'll begin with triangle ABC, so a very generic triangle, nothing special about it. And we'll extend one of its sides through a vertex. So as you can see, we've extended side AC through C to a point D. And we'll prove that the exterior angle created, that is BCD, is greater than one of the remotes. And that's all that we'll do. We'll prove that one exterior angle of a triangle is greater than one of its remotes. And this is certainly one of those rinse and repeat kinds of situations. The way that one would prove that any exterior angle, any other exterior angle is greater than either of its remotes would be precisely similar in form. So you'd have to do it only once. So it begins with a set of constructions that are far from obvious. This is typical of Euclidean geometry. The way in which Euclidean geometry is often very difficult is that to solve a particular problem, constructions must be added to a diagram, but initially what those constructions should be is far from obvious. Here we can only thank Euclid, or whatever ancient geometer first was able to develop this proof. we can thank them for the construction. So here's what we do. So first of all, we construct the midpoint M of side BC, and then we construct a segment through M to a point Z such that AM is equal to MZ. So it's as if we take a segment to M and then we continue that segment a distance equal to that already gone. So we end up with the segment AZ with M its endpoint. And then finally we construct the segment ZC. And these are all familiar constructions. These are constructions that are allowed. They've all been discussed before. So how does one then prove that the measure of angle BCD is greater than the measure of angle B? Well, it begins with congruence. So consider triangles AMB and ZMC. It's clear from the diagram, because we have M the midpoint of two segments, both of BC and AZ, that two sides of AMB are equal to two sides of ZMC. So we're 2/3 of the way to triangle congruence. And as for what else we know about them, well, of course, the vertical angles theorem is still very much true. So we have a pair of equal vertical angles. So I will, if I can, I will mark that. So there we go. I'm able to mark that. So we have a pair of equal vertical angles, marked well enough, I suppose. And then, of course, we can say that the triangles are congruent by side angle side congruence. It now follows by CPCTE that angles ABC and BCZ are equal to one another. So I occasionally do this. I'll just put, how about some stars on either one, just to sort of bring attention to them. It then follows, as I said, by CPCTE, that those two angles must be equal to one another. Now consider the relationship of angle BCZ to angle BCD. Might be good to sort of indicate where those are. So here is, it's a bit sloppy, but there is BCZ, and here is BCD. Let me erase that. So hopefully you can see that well enough. Should be clear that BCZ is part of BCD, which means, by a theorem proven in a previous chapter where we said that the whole is always greater than the part, that the measure of angle BCD is greater than the measure of angle BCZ. But recall that BCZ was equal to angle APC, so it now follows that the measure of angle BCD, which is the exterior angle, is greater than the measure of angle ABC, that is angle B in the triangle, and then the conclusion follows. All right, now on to the parallel tests. So I'm about to show you how it is that the triangle exterior angle inequality allows us to conclude that if certain conditions are met, lines must be parallel. So here's the first. This is the first and primary. We'll prove this one by means of the triangle exterior angle inequality, and then this result, the alternate interior angles test, will be used to prove the other tests. Okay, so here's the result. If a transversal cuts a pair of lines, and I'll just go ahead and hop over to the result instead of the general description. If a transversal cuts a pair of lines and forms equal alternate interior angles, then those two lines are parallel. Okay, so you see here the importance of the transversal. Okay, as I said in the previous lesson, what the transversal does for us is it creates angles, in particular special angle pairs like alternate interior, and we're now about to use that. Okay, so the result again is this. If a transversal cuts a pair of lines that I don't know are parallel to begin with, so that alternate interior angles are equal, then those lines must be parallel. Okay, so this is a parallel test. That is, if we pass the test of equal alternate interior angles, it follows that our lines must be parallel. All right, so here's an illustration of what it is that we're supposed to prove. Our two lines are M and N, and our transversal is T. And this forms alternate interior angles 1 and 2. So the result is this. If the measure of 1 is equal to the measure of 2, then it follows that the lines are parallel. Now, how is this proven? Indirectly. That is by contradiction. So let us assume then that though we have a pair of equal alternate interior angles, our lines are not parallel, and from this we'll be able to derive a contradiction, which means, of course, our original assumption is false, which gives that the lines are parallel. So think about this for a moment before I show you the diagram. We're supposed to prove that lines are parallel, and we have assumed that they're not parallel. So if they're not parallel, what happens? Well, of course, what happens is that they must intersect. So let us show them to intersect. So we assume that M and N are not parallel, which means that they intersect. And ask yourself then, what gets formed? Should be clear that we get a triangle. Okay, one side lies along T, another side along M, the third side along N. We get a triangle. And then notice that we can use the old language, not that old, but the previous language, of exterior angles and remotes. If lines M and N meet, then angle 1, they might have met on the other side, but if they meet on the right side, this will mean that angle 1 is an exterior angle and angle 2 is a remote. And then at this point, we can invoke the triangle exterior angle inequality and declare that angle 1 must be greater than angle 2, but that contradicts the given. The given was that the measure of 1 is equal to the measure of 2. So it follows then that we have reached a contradiction, which means the assumption that M is not parallel to N must be false. That is, M is parallel to N. Now, with the alternate interior angles test in place, we can prove the other tests relatively easily. And in their proofs, we will build upon the alternate interior angles test. There will be no need to revert back to the method of contradiction. And as we prove these theorems, we'll call upon some core theorems from previous chapters. Here's some quick reminders. The result that linear pairs are supplementary, that vertical angles are equal, and that perpendicular lines form 4 right angles. Those are some of the most important sort of basic theorems that we proved in a previous chapter, and they will be invoked here and also in multiple other locations later on in the class. So here's an example. I won't go through all of the tests on the problem set for today. You will actually prove a number of other tests, but here is one of them, just as an example of how it is that these results will be proven. And it says this: if consecutive interior angles are supplementary, then lines are parallel. And this is our consecutive interior angles test. So you can see the setup here. We have a pair of lines M and N with a transversal T, consecutive interior angles 1 and 2, and we are given that they are supplementary, and we wish to prove that the lines are parallel. Okay, so how do we do this? Well, let's add an angle name. So angle number 3. Of course, we're free to name angles as we see fit. And then let's think about the relationship between angles 1 and 3. They are, of course, a linear pair, which means that they are supplementary. And then what we have is this, is that 3 is supplementary to 1, but also 2 is supplementary to 1. That's the given. That is, both 3 and 2 are supplementary to 1. And what do we know about angles each supplementary to the same third angle? That's the same supplements theorem. They are equal. So it now follows that angle 2 is equal to angle 3. And now think about this through the lens of the work that we've done in this chapter about parallels. Angles 2 and 3 are alternate interior angles. So we have now concluded that a pair of alternate interior angles 2 and 3 are equal to one another, from which it follows by the alternate interior angles test that our lines are parallel. So see how we made use of the alternate interior angles test. And then finally, final matter. With the tests proven in this section, we will have a new construction. Okay, and remember what constructions are. Constructions allow us to assert the existence of something that hasn't already been given or it isn't already mentioned. Like for instance, I don't know, if we're given a segment, then we know that the midpoint of that segment exists. As we discussed previously, that follows by ultimately the rule of postulate. And that means we can mark it. That's something that we can add to the diagram. Now in this case, what we'll be able to construct is a parallel. And here's what we have to be given. We have to be given a line, in this case, in this diagram, M, and a point not on it. That's the point P. Our new construction rule will tell us that we may construct through P a line parallel to M. We are guaranteed of the existence of such a line. Okay? And this, as we've talked about before, whenever we introduce a new kind of construction, we must always have a justification for that. We must always have a proof for it, a proof of the existence of the object that we say that we may construct. And with the tests in place, in particular the alternate interior angles test, we have a guarantee of the existence of this. And let's actually talk about how it is that one would do this. Okay, and I'll show you in a moment, but let me talk you through it. So first of all, you'll choose a point Q on M, and then you'll construct a line PQ, and then you'll construct a line through P so that we get alternate interior angles equal. Okay, and I'll talk, as I actually show you on the next slide, about why it is that all of these are allowed. But what you'll end up with then are two lines and a transversal so that alternate interior angles are equal, which means that lines are parallel. Okay, so what does this look like? Okay, so let's actually carry through the steps here. So we'll pick a line, or pick a point Q on our line M. Okay, so here is a point Q, and then we'll construct the line PQ. These are all allowed constructions, of course. If we have 2 points, we may construct the line through them. And then, of course, that gives us, I'll mark this at a different color, that gives us an angle. Okay. And then let us construct a line through P so that we get that same angle measure, but on the opposite side. Okay. So what we're really about to do is to create an angle of a certain given measure. And that, of course, is something is allowed by the protractor postulate. The protractor postulate says that if we have a certain measure in mind, a certain angle measure in mind, we may construct an angle with that measure. So what we do at this point is we construct that line through P. Okay, so here's the line through P, we'll call it N, so that, okay, here's the construction rule that we previously have, so that the angle formed on the opposite side of what is now the transversal is equal to that angle that was formed on M. Okay, so all the construction steps that I've done are completely allowed. Choose the point on M. A line is just a collection of points, so we can choose a point wherever we wish. Construct the line PQ. Now construct the line N so that we get equal angles as shown. And then once we've done that, what we have are 2 lines, M and N, with a transversal, line PQ, so that alternate interior angles are equal, which means that line M is parallel to line N. So what we're now allowed to do is this. If we ever have a line and a point not on it, then we may, if we wish, through that point, construct a line parallel to the given line. And this will be absolutely crucial for us in the work that we do later in the chapter. As a matter of fact, it will be the crucial first move when we prove the triangle angle sum theorem, and that is definitely on the horizon.